Alright, grade 9, so welcome back to 6.4, similar triangles. So last episode, 7.3, we talked about similar polygons, similar shapes, and how the lengths of the shapes changed, and they were proportional because they all had a scale factor that we talked about in 7.1. However, the angles don't necessarily change if you have the same scale factor. So what we're going to do now is we're going to lean into triangles. Okay, a lot of triangles will be similar, but the proportions will be changed. Therefore, their angles are the same. So our learning goal, our learning intention is to recognize and draw similar triangles and then use their properties to solve problems. What you have to know is that corresponding angles are the same and corresponding sides are proportional. So there's a ratio in between there, and which is called the scale factor. So the success criteria for you with respect to the learning goal of drawing similar triangles and using their properties would be able to reiterate that the angle doesn't change, but the proportion is found by a ratio. Like here we have triangle ABC, which we have sides 3, 4, and 5, and then we have triangle X, Y, and Z. We have side 12, 16, and 20. Now, if you were to measure these out, as stated in previous videos, I don't have a protractor app for this, but this angle here, angle X, is actually the exact same as angle A. Okay, because 3 multiplied by 4 is 12, 5 multiplied by 4 is 20, and 4 multiplied by 4 is 16. So therefore, the corresponding sides are proportional, so they have the same proportions, they're just multiplied by a scale factor, all the same number, of course. So that means that the angles are the same. So angle A equals angle X. And this was 66 degrees. So therefore this would be 66 degrees. So we had angle A was 66 degrees. Whoa, 66 degrees. Therefore angle X, which is the same, would also be 66 degrees. Angle B, well, this is a right angle triangle, so it appears, and it will be. If it doesn't have a box, you can always use your protractor to figure that out, that this is 90 degrees, and so therefore this would be 90 degrees. Now wait a second. If I were to just use a calculator here for a second, well, I know that all triangles have 180 degrees. 180 minus 90 minus 66 will give me my other angle 24. Okay, so we have 24 here and 24 here. Okay, so that's really the key to recognize, that the angles are the same although the side lengths are different. Now, let's just take this back to this ladybug diagram here where we talked about the dimension of the scale diagram. So the new one divided by the original diagram will let you find your scale factor. So we found out that the ladybug was 6, and then the original was 3, sorry, 2. So 6 divided by 2, the new divided by the original, would be our scale factor. Well, how can we tell what our original one is? Well, let's think about our alphabet. So A, B, C, D, L, M, N, O, P, P, Q, R. So P, Q, R, that would be the first triangle. Okay, and then R, S, T, okay, would be our second triangle. So if we compare these, technically, angle Q, we're keeping in mind that these are similar triangles, angle Q would be the exact same as angle S. Angle T would be the same as angle P. Angle R is the same as angle R. Okay? So, now let's take a look at our fractions here to figure out if our scale factor is actually fully correct. So if I took the original measurements here, so if I took side QR which would be 6. I took side QP, which is 4, inside PR, and then I left those as the denominators because those were the originals. And then I put in the dimensions of the new scale diagram. So I put in, so for TR, that's corresponding with the 5. So 7.5 over 5. Then they have SR, which is corresponding with QR. So 9 over 6. And then lastly, TS is corresponding with this QP. So these are proportional. So these are proportional. These are proportional. And these are proportional. And the angles are the same. Now, is this actually a similar triangle? Let's figure out if the scale factor works out. 9 divided by 6 is 1.5. 6 divided by 4 is 1.5. If this is the answer is 1.5, we do have a similar triangle. 7.5 divided by 5 is 1.5. Therefore, I can conclude that all these angles are the same. If the scale factor is the same and they're proportional, you can then say these angles are the same. Just to reiterate, if the corresponding sides are proportional, the angles are the same. Now let's just take this to a greater concept here. So we want to find the length of this lake here. And we actually have indicators. So we have this sine and this sine. So that's like telling us this angle and this angle are the same. And this angle and this angle are the same. Well, I have this side length here for the small original triangle. And I have this side length here. Well, let's see if I have something with the bigger triangle. Well, I actually do. I have this full side because I have both measurements. 305 and 210 together would be 515 meters, of course. So let's figure out that ratio. So if I had 515 divided by the original same side, original corresponding side, which is 210, I would get a decimal answer. I think it's 2.45. That's not a good looking for. That's 2.4524. I'm going to 4 decimal places because there's nothing wrong with being more precise here. So 2.4524. So we're assuming here, because we have a side, we have 2 angles in the side, that we do have a similar triangle here. Now, when it comes to finding out what this side would be, well, I would take the 230 meters, so 230 meters, and multiply that by the scale factor of 2.4524. So let's do that. So 230 multiplied by 2.4524. So it's 564. 64.052. Let's just round here for 2 decimals at the end. It's sometimes better to go 4 decimal places because you're more exact. I know if we just multiplied 230 times 2.45, we're going to get 263.5, but this is a more correct answer. So what is the length of this lake? Okay, so the lake is that amount of meters wide. Okay, and that's how we solve problems with similar triangles.